The story of space weather begins, of course, at the sun. So the sun has an atmosphere, but it's completely different to the atmosphere here on Earth. The gas is at around 1 million degrees or higher, which means it's not actually a gas, it's a plasma. So it's an ionized plasma where you have electrons and protons whizzing around and not many neutral atoms. The plasma, being charged, is trapped within the strong magnetic field, which pops out from the surface of the sun and permeates the solar atmosphere. So it's a strange place. The gas is forced to move with the magnetic field, and in some places the magnetic field is forced to move with the gas. Completely different, as I say, from Earth's atmosphere. Being hot and surrounded by the so-called vacuum of space, the sun's atmosphere expands constantly to fill the surrounding space. So, accelerating outwards to several hundreds kilometers per second, this forms the solar wind. Solar wind fills and defines the solar system, ending in the heliopause. So we consider the planets, including Earth, are orbiting within the extended atmosphere of the sun. And things that happen near the sun can affect us here on Earth. And this is called space weather. I'm showing in the movie here a huge eruption of material from the sun's surface. The magnetic field gets twisted by motions into configurations it really doesn't like. So you can imagine twisting an elastic band, and then you reach a breaking point and the whole thing erupts rapidly. And this is exactly what happens here. And it results in a huge cloud of magnetized plasma with a mass of several Snowdons, to use a Welsh scientific unit. This whizzes out at anything up to a couple of thousand kilometers a second into space, and some of them may encounter Earth. And these are the major events in space weather. So, do we need to be scared? Not really. From a health standpoint, humans on the surface of Earth are safe, nature is safe, our atmosphere is stable from these events. And that's because we have an extended magnetosphere on Earth, which acts like a shield. So when these huge events, when the solar wind carries these coronal mass ejections, CMEs, out and they encounter Earth, they hit Earth's magnetic field and cause disturbances in Earth's magnetic field. But they are prevented from disturbing our lower atmosphere because of the magnetic field. So, Earth's magnetic field will rebound, it will oscillate, it will reconnect or reconfigure, and this allows injection of solar wind material into Earth's magnetosphere. So you can imagine the magnetosphere like an isolated pocket sitting in the solar wind, but occasionally you can have injections of material. And this causes the beautiful aurora, the northern and southern lights, this injection of material. And when that material plunges down the magnetic field lines surrounding Earth to high latitudes, and they smash into molecules in Earth's lower atmosphere and cause these beautiful colours. And that's one of the nicer effects of space weather. What space weather does is affect modern technology and infrastructure. So this includes GPS systems, so it can disrupt the GPS process. It can harm astronauts. It can damage satellite components. And when you consider the cost of one satellite, that's quite a substantial cost. It can affect the orbit of satellites, make them unpredictable. And for airline flights which pass near the poles of Earth at high latitude, there's an increased risk of radiation dose. The passengers will probably be fine, but it's the staff on that flight that might make that flight several times a week over the course of a year. Well, are they building up substantial radiation doses? And the one that causes a lot of concern as well are power grids. So as Earth's magnetic field is being wobbled by these disturbances in space, the magnetic field enters the rocks underneath our feet, and this movement of the magnetic field creates electric currents in the ground. And over long distances then you can build up large potential differences or large electric fields. And when you consider the power grids, these pylons and the wires are going for hundreds of miles before being grounded at substations. You can have large rapid changes in the potential differences between the two substations, and that can cause unexpected damage in very expensive and very hard to replace components in the substations. So that's a major concern. And especially in Wales, the two main power lines of the national grid follow the north and south coasts of Wales. So they're going east-west, which makes them more prone to damage. And also the rocks, the nature of the rocks we have underneath our feet in Wales makes it more prone. So, one big thing we can do to reduce or to mitigate against this damage is to forecast these events. So just like we're anticipating a big storm on Earth, having that few days warning can make a huge difference to the damage that storm will make. And currently at the UK Met Office, there's a space weather team. There's around 15 forecasters working, and they man the space weather station in the Met Office down in Exeter 24 hours a day. They are trained to look at images such as these from various space-based telescopes. So they stare at images of the sun, they look for these rapid changes, these CMEs, these explosions, and they are trained to say, well, this explosion is likely to hit Earth, this one isn't. Okay? And they can make a rough estimate of the velocities of these storms, how fast they're traveling, and give a rough time of arrival at Earth. But they really can't say much more than that. There are things within these eruptions, for example, the orientation of the magnetic field, that have a huge effect whether they will have an impact on Earth or not. And currently, space weather forecasting is really in its infancy compared to Earth weather forecasting. In Aberystwyth, we're leading a UK-wide project to improve the software the Met Office uses, and we're bringing in more automated methods for measuring and characterizing these explosions. And hopefully in the next year or two, this software will be up and running at the UK Met Office and make the life of the forecasters a little bit easier, and also give better time of arrival estimates for these events. Currently, it's like, oh, we're likely to have a CME impact Earth within the next day or two. So there's like 12-hour, 24-hour uncertainty, and really that's not good enough when you're asking an airline to cancel flights, or you're asking the military to stop doing some exercise or something like that. So we've got observations near the sun. We can characterize these huge eruptions. We can plug them into a model of the interplanetary space, and we can have an estimate of the impact on Earth. The next decade or so for solar wind, for space weather mitigation depends critically on four things. The first is to improve observations. We need to have more spacecraft out there taking more different types of observations of the sun. And really, without that, we can't really improve forecasting. Luckily, there are a couple of new missions that will be launched in the next few years, which will make a big difference. We need more funding for blue sky research to understand what's going on in the solar corona. I said earlier in this talk that it's an alien, extreme environment, not easily replicated in laboratories. So we need more research to understand the processes and the mechanisms going on in the solar atmosphere. And that can help us to give more warning time before these events occur. We need better forecasting tools, and I think over the next decade or so, we will look at machine learning coming increasingly important in forecasting. And lastly, it's the actual resilience of systems here on Earth. And there's a lot being done to for example, to make GPS less prone to space weather events. And if you have dual channel GPS, it works pretty well, even in the case of severe space weather. I think the biggest problem is developing countries. They need support and resources to make their power grids and systems resilient. So, I'd like to finish this talk with something more scary and talk about the Carrington event, which most of you have probably heard of. So, the Carrington event occurred in the 1850s, and to date it's the largest solar space weather event we know of. It was so powerful, the aurora could be seen down to equatorial regions. So people in Cuba saw the northern lights. The northern lights were so bright in the UK, apparently people could take a book out at night and read by the light of the aurora. And at that time, of course, they didn't have the dependence on technological systems we have now, although several telegraph offices were reported to burst into flame. So if we had a Carrington type event occurring tomorrow, would we be in trouble? Do you need extra life insurance? No, you would not be harmed at all. Nature would not be harmed. But it's likely there will be power cuts in many regions. And as I said, GPS, radio communication, radio blackout. So yes, it would cause a problem, but I don't think it would send us back to the Stone Age or anything like that. The problem with this is events of the Carrington scale occur so infrequently, we really don't know the statistics, which makes judging when the next one will occur very difficult. And also it makes judging the size likely, can it be worse than the Carrington event? It's also impossible to say. Many people have estimated that the Carrington event is a once-in-a-century event. So we're half a century overdue. It's what's called a black swan event in statistics. It's happens so infrequently you don't have the statistics to do much analysis. So don't lose any sleep. Don't phone your insurance company unless you own several satellites or something like that. But this concern, this urgency really drives the field of space weather research, and is one of the reasons I love doing it. Thank you.